You know that feeling when you're looking at a math problem and you see the same two numbers written in like 5 different ways? It's confusing, right? Well, today, we're going to dive right into that. We're going to decode the mystery and actually learn to speak the language of vectors.
It usually starts with something that we all recognize, a comma. We've been seeing this since we first learned to plot points on a graph. Simple enough.
But then, bam! You see this. Same numbers, 3 and 2, but now they're in these slick angle brackets. Is this different? Does it mean something else?
And then maybe you're in a computer science class and this pops up. Square brackets, a space, laid out flat like a row. Okay, another one.
And just when you think you've seen it all, you get this. A column. The same two numbers, but stacked on top of each other. It's enough to make you scratch your head.
So what is actually going on here? Are these all just different ways to write the same thing? Or is there a deeper meaning behind each one? That is the question we're going to get to the bottom of right now.
Okay, so first things first, we need to get our heads around the fundamental difference in what these numbers can even represent. And it all boils down to a really simple story, a tale of a place versus a journey. A point. That's easy. It's a location, a static spot. Think of it like an address on a map. It tells you where something is. But a vector, on the other hand, is all about movement. It's a journey. It has a size, how far you go, and a direction, which way you go. It tells you how to get somewhere. Now check this out, because this image shows both ideas at once, which is really cool. We can look at 3, 2 and see it as the destination, the dot. That's the point. Or we can see it as the arrow, the journey from the starting line to that dot. That's the vector. Same numbers, same final spot, but two totally different ways of thinking about it. So it really all comes down to this one simple line. Honestly, if you remember just one thing from this section, make it this. It's the perfect way to keep them straight in your head. A point is the where. A vector is the how.
And this is a huge idea. A vector isn't nailed down to one spot. That arrow is basically a set of instructions. Move right 3 and then up 2. You can start following those instructions from the center of the graph, or you could start from that point, 1, 1, or literally anywhere else. The journey itself, the vector, is always the same.
Okay, so a point is a location, a vector is a movement. Got it. But here's where things get really interesting. What if I told you that the idea of movement has been secretly hiding inside the coordinates of a point this whole time?
So how does that even work? Well, just look at the point 3, 2. Those numbers aren't just a label, they're actually a recipe. They're telling us, start at 0, take 3 steps in the standard horizontal direction, and then take 2 steps in the standard vertical direction. So getting to the point 3, 2 is just combining those 2 basic movements.
And that, right there, is the big aha moment. The coordinates we use to label a point are not just random tags. They are fundamentally instructions. They tell us how much of each basic direction we need to mix together to get to our destination. This is why points and vectors are so deeply connected.
So, if they're so closely related, that brings us back to our original mystery. Why all the different symbols? Well, let's crack the code. The answer is that notation is a language, and just like in any language, good authors choose their words or symbols very carefully to emphasize a particular meaning.
Think of this table as your official decoder ring. Those familiar parentheses, they usually signal we're talking about a location, a point. Angle brackets, super common in physics, really emphasizing that idea of a directed journey. Square brackets often just mean a list of data in programming. And then you've got the row and column versions, which are absolutely critical in linear algebra. It just goes to show you, context is everything.
Now, let's zoom in on this row versus column thing, because this one trips a lot of people up. You might look at them and think, same numbers, who cares? But in the world of matrices, their shape, horizontal versus vertical, is a huge deal. They are not the same thing at all. And here is a perfect example of why. When you start doing matrix math, the shapes literally have to fit together like puzzle pieces. See how that column vector with its tall, skinny shape slots right into that multiplication? It just works. Now try to jam a row vector in there. Nope, it won't fit. The math breaks. So the choice isn't just for looks, it's completely functional. So we've pretty much cracked the code for 2 dimensions. But the real power of vectors, the reason they're everywhere in STEM, is that they let us go way beyond what we can just sketch on a piece of paper.
Moving up to 3 dimensions is pretty much what you'd expect. We just add a third number for that z-axis, coming out of the page.
So the point 345 just means go 3 in the x direction, 4 in the y, and 5 in the z. All the same principles we've been talking about still apply.
But now, for the real mind bender. At its core, a vector is just an ordered list of numbers. So what about a list with 5 numbers? We can't draw it, we can't picture it in our heads, but we can absolutely do math with it. And that's why vectors are the absolute bedrock of fields like data science and AI, where you might be juggling data with hundreds or even thousands of dimensions.
So, let's bring it all home. What's the big takeaway? Here's your new reading strategy. The next time you see a list of numbers wrapped in some kind of brackets, just pause for a second. Ask yourself, is this an address or is it a journey? What is the author trying to emphasize with this specific notation? Does the shape, row, or column matter here? Answering these questions will help you truly read the math, not just see it.
And that really gets to the heart of it all. Mathematical notation isn't just a bunch of random squiggles. It's a rich, precise language. So don't just skim past it. Take a moment to read the meaning that's been carefully encoded behind the symbols. Ask yourself, what story are these numbers trying to tell me?